Alright, we'll see how this takes. Again, somehow this program's having a problem with this thing off on the left, so we'll see what we got here. I'm going to push this out temporarily and then redraft it when I get a better capture engine. So we're looking at trusses here, and we want to see that this is all the same form of problem. Trusses and beams, cables, they can all be solved with the same basic set of methods by adding vectors together, sliding them along their line without adding a couple, or perpendicular to their line of force by adding a couple. We can use spreadsheets very effectively, and we can use CAD very effectively. What we generally want to do is solve for the reactions and then solve for the internal forces at any and all places as is necessary to evaluate the structure. Okay. In terms of trusses, here's what you do. You solve for the reactions, and then you do a section cut that generates no more than 3 unknowns of known directions. Remember the geometry. That layer or that information gives you the geometry of the force. Show all your unknowns as tensions. If you have them, you can simplify them all into one force vector for determining reactions or even for determining internal reactions. Very often you can shift that force vector pair to your chosen concurrency point. Again, you don't need to do these things with trusses, but you could. And then determine the magnitude of the tension vector for the unknown truss member that is not concurrent to your chosen point. So if you start shifting vectors to the concurrent point and then generate moments as you shift those vectors, there's going to be one force out there that's going to have a moment, and you can then solve for that force. Once you have that force, you're left with 2 unknown forces. And so you can just basically do a concurrent force problem by knowing that you have 2 unknowns of known direction and a sum of known forces, one of those forces being the reaction in that other truss member you just solved. And so you just have basically the unknowns are the opposite of the knowns. We'll go through this again quickly. Typical structure, all kinds of ways to solve for the reactions. You can slide vectors. The only place this comes up to be an issue in trusses is very often you're going to need more often to do a weighted average because all of your vectors are going down or up typically on a lot of truss problems. Right, you end up with one sum of the applied forces. You can then solve for the reaction forces by realizing the moment about the left side has to be equal to 0. So you have the applied moment and then you have a reactive moment. You do the same thing about the right side. And of course you could have used that basic rule that if once you knew the line of force for the resultant of the applied forces, that the 3 forces have to be concurrent. Very often on a PowerPoint or on a sheet of paper you run out of room, but it is a good, logical, and effective solution, especially if you're working within CAD. Well, of course, this is all just the same thing as calculating the sum of the moments about any one point and having it equal to 0. You notice here that R4 and F4 are our reaction forces, which you typically are solving for. So you know R4, but you're solving for F4, but you know its direction. And of course, the general form of this equation is that you can have as many forces as you would like. Another way, of course, is to just do this with a spreadsheet or with vector mathematics, and remember that any force vector is defined by its starting point and then its delta. And if we have our origin down there at the bottom left, R cross F1, R cross F2, R2, F2, cross of R3, F3, and the cross of R4, F4 all have to equal to 0. And that, of course, is what we've seen before. And another way to look at this, of course, is that the reactions are the opposite of the applied forces. All you got to do now, once you solve for the reactions, assume you know the reaction at x4 or y4 or at the other support is, you try to find, if you can, a side of the structure that goes through the forces you want to determine that only has one force on it. If it has two forces or three forces, you can once again add them up graphically. But once you do that, you can do a shift, most easily shift your origin mathematically to the new point of concurrency, or a point that takes two of the forces out. Solve the sum of the moments, or just a force times distance more or less problem, and then you're left with two forces and two unknowns, and you can solve it as a concurrent force problem. All that is all possible quite easily with the aid of spreadsheets, but very often it can be done pretty quickly and efficiently and close when you do it by just using graphics or a combination of graphics and math. That's the end of the slideshow. We will recut this and use it in class along with a few others, especially as we compare it to doing a graphical solution with a cable and with a bending member. Thanks for listening.